Hello everyone, I'm Danning from Purdue University. Today I'm going to give a talk on our paper, DocTer, Documentation Guided Fuzzing for Testing Deep Learning API Functions. Deep learning systems have been widely deployed in many applications, such as self-driving cars, machine translation, and cancer detection. As a result, the reliability and security of deep learning systems are of vital importance. However, it remains challenging to test deep learning systems, as deep learning systems are often complex and it is hard to generate valid inputs. Invalid inputs will not pass the code validity check and result in exceptions. For instance, in this calling to a PyTorch API as threaded, which sample the input value with certain thread. It throws an exception saying that the argument input should be a tensor instead of a list. A tensor is a type of data structure representing a multi-dimensional array. The exceptions prevent us from reaching the core functionality and testing the function deeper. Therefore, to test core functionality of deep learning APIs, we need to generate valid inputs with the correct data structures. After generating inputs with tensor data structure, the function call can be executed with no error. Let's take a look at another example. Here, in the TensorFlow API max pool3d, which conducts pooling operation for the input tensor, we generate a tensor for the parameter input. However, it throws an error saying that the input should be 5-dimensional. After we pass the parameter input with the correct dimension, we pass 0 for the required parameter padding to enable zero padding. However, we got another exception saying that the parameter padding should be either same or valid. Therefore, to generate valid input for deep learning APIs, other than data structures, we also need to know the properties of these data structures. Without such knowledge, most of the inputs will simply trigger exceptions in the code validity check without reaching the core functionality. Although generating inputs for deep learning APIs is challenging, our observation is that some of the input constraints are described in the document. So, our solution is to extract constraints from the document to guide the input generation. While the existing techniques can extract constraints from code or software text, such as comments or documents, they are insufficient for extracting deep learning specific constraints. To generate valid inputs, we designed a tool, DocTer, to extract constraints from document automatically. For example, in this document, it says that the parameter input should be a 5-dimensional tensor. DocTer extracts these constraints and represent them in this formal representation. Due to the time limit, I won't go into the details. They can be found in the paper. Then, DocTer generates a 5-dimensional tensor based on the constraints. Parameter case size should be an integer or a list of integers that has length 1, 3, or 5. We extract the constraints and generate case size as a list of length 1 with only one element 0. We do the similar thing for parameter strides. Lastly, for parameter padding, according to the document, it has to be either valid or same. We extract the constraints and generate valid for padding. Finally, DocTer calls the API with these input parameter values. This particular input will trigger a floating point exception crash in TensorFlow. We apply DocTer to TensorFlow and extract 5,908 constraints from 911 TensorFlow API documentation. Thanks to the constraints, DocTer is able to generate valid input to pass the code validity check and trigger this floating point exception. We reported this crash on GitHub, which is later confirmed and fixed by the TensorFlow developers. Here are our contributions. We designed and implemented a novel rule construction technique to build rules that map syntactical patterns to parameter constraints, and a novel fuzz testing tool, DocTer, that extracts 4 categories of constraints from API documentation to guide the input generation for testing. We also evaluated DocTer on 3 of the most popular deep learning libraries, TensorFlow, PyTorch, and MXNet. DocTer is able to extract 16,035 constraints for 2,415 APIs from documentation with a precision of 85.4%. DocTer detects 94 bugs in 174 APIs, including 63 unknown bugs and 1 previously unknown CVE security vulnerability. We released the source code of DocTer, the dataset, and the bug list. Next, I will introduce our approach. Here is the overview of DocTer. DocTer consists of 3 phases. First, DocTer constructs rules from a portion of the API documents. Second, DocTer applies these rules to extract constraints from the API documents automatically. For example, from a TensorFlow API, it says that the parameter value should be a 4D tensor of type float. DocTer detects constraints-related patterns and applies rules to extract constraints. Finally, DocTer generates test inputs guided by the constraints and execute the input to detect bugs. Next, I will introduce each step in detail. Before it starts, DocTer performs 2 preprocessing steps to the document text, normalization and dependency tree parsing. For example, in this description for parameter max filter, it says a tensor of type float32. We first normalize the sentence by replacing the structure type keyword tensor with D structure and data type keyword float32 with D type. Normalization helps DocTer to reduce the variance of text and focus on the syntactic patterns. Then, the dependency tree parser will convert the normalized sentence to a parse tree using an open-source NLP toolkit. By doing the above preprocessing steps, DocTer converts free-form API descriptions to dependency parse trees. The parse tree highlights the syntactic patterns of a sentence and helps DocTer to discover and construct rules. The next step is rule construction. According to prior work and our study, we found that the simple graph-based or manually defined heuristics generally do not work well for this problem. Therefore, we designed a general approach to construct rules which could extract constraints automatically. Since it is hard to analyze all the text, we want to start with the frequent cases and construct rules from them. We first conduct frequent subtree mining to discover frequently occurring subtree patterns. In these examples, the subtree pattern of type D type is one of the most frequently occurring subtrees in all of the documents we analyzed. To construct the rules, we manually annotate a small portion of the document with the ground truth constraints. Then, our rule construction component identifies a rule that maps the frequently occurring subtree pattern of type D type with the data type D type. We then construct a rule that maps the subtree to the constraint. From this step, DocTer is also able to construct these 2 rules as well. Due to the time limit, I won't go into the detail. Then, DocTer applies these rules to all of the preprocessed API documents to automatically extract constraints. For example, given this sentence, a 4D tensor of type float, we first conduct normalization and dependency tree parsing to this sentence. Here, we replace the constant number 4 with the annotation constant num. The parse tree contains 2 frequent subtrees. These 2 subtree patterns correspond to rules 1, 2, and 3. DocTer applies these rules and obtains the constraints for the parameters. Then, with reference to the original document, we reverse the annotations to the concrete constraints. For example, D type mapped to the word float in the original document, so we extract the data type as a float. To demonstrate the effectiveness of these extracted constraints, we implemented a fuzzer to generate test inputs, either conforming or violating the constraints, and executes the input to detect bugs. Here are our experimental settings. We evaluate DocTer on 3 most popular deep learning libraries, TensorFlow, PyTorch, and MXNet. We collect 2,558 relevant deep learning library APIs to apply DocTer on. After the constraints are extracted, we generate 2,000 inputs for each of the APIs. On average, it takes 0.14 seconds for DocTer to generate and test each input. Here are the evaluation results of constraint extraction. DocTer is able to extract constraints from 2,415 APIs with 1,338 automatically constructed rules. There are 16,035 constraints extracted in total. On average, DocTer extracts 6.6 constraints per API. We manually sampled 603 parameters and annotated them with the ground truth constraints for evaluation. The results show that the constraints DocTer extracted achieve a precision of 85.4%. To evaluate DocTer for bug detection, we compare DocTer with the baseline method. We implement an unguided input generation tool as the baseline. The only difference between DocTer and the baseline is that the baseline has no knowledge of the constraints. We choose to implement our own baseline because the existing fuzzers either have no knowledge of the constraints and cannot generate deep learning specific structures, such as tensors, or they require manually encoded test inputs. This table shows the number of bugs detected by DocTer for each library. In total, DocTer is able to detect 94 bugs in 174 APIs, while the baseline can only find 59 bugs. 63 of the 94 bugs are unknown bugs, and 54 of the 63 bugs have been confirmed or fixed by the developers. We only consider crash, including segmentation fault, floating point exception, abortion, and bus errors. To test the API's functionality and the input validity checking code, we design CI and VI modes. Here, CI means conforming input, meaning we generate inputs following the constraints. VI stands for violating inputs, where we generate input violating the constraints. The conforming inputs are designed to test the core functionality of API function, and the violating inputs aim to test the API function's input validity checking code. We generate 2,000 inputs for the baseline method and 2,000 inputs for DocTer. Among the 2,000 inputs for DocTer, 1,000 of them are conforming inputs, and 1,000 of them are violating inputs. We set the conforming ratio to 50% based on a study on a portion of sampled API. The details can be found in the paper. Here in the table, we show the breakdown of the results in each mode. The results show that CI and the VI mode alone, with only 50% of the inputs, are better than the baseline, or they can detect more bugs than the baseline. Having the constraints enables DocTer to generate inputs conforming or violating the constraints. Without the constraints, one cannot generate CI or VI. With the constraints, DocTer is able to detect this new PyTorch bug from an API average pool 2D. By analyzing the document, DocTer generates a tensor for parameter input and zero-dimensional integers for parameter kernel size and stride. This input triggers a floating point exception crash in PyTorch. We reported this to GitHub. This issue has been marked as high priority by the developers, and it is later fixed by the PyTorch developers. In conclusion, we propose DocTer to automatically extract constraints from deep learning API documentation to guide the input generation for testing. We evaluate DocTer on 3 of the most popular deep learning libraries, TensorFlow, PyTorch, and MXNet. DocTer extracts 16,035 constraints automatically from 2,415 API documentation with a precision of 85.4%. DocTer detects 94 bugs in 174 APIs, including 63 unknown bugs and 1 previously unknown CVE security vulnerability. We make the source code of DocTer, the dataset, and the bug list publicly available. Thank you for listening.